Inferential statistics is about using data obtained from a sample to make conclusions about the larger population from which the sample is drawn. In this section, we'll learn about a fundamental technique for inferential statistics, hypothesis testing. This involves formulating a hypothesis about some parameter of a population and constructing a confidence interval from a sample to determine whether the hypothesis should be rejected or not. The first step in hypothesis testing is to formulate two complementary hypotheses: the null hypothesis H0, which represents the status quo, and the alternative hypothesis H1, which is the logical negation of a null hypothesis. Usually, each of these hypotheses is in the form of a comparison of some population parameter to a specific value. For example, the null hypothesis could be that a mean is equal to 0, and therefore the alternative hypothesis is that it is non-zero. The alternative hypothesis H1 typically represents a conclusion that a researcher hopes to support with evidence, which tends to be a departure from the status quo. For this reason, it is natural to actually state H1 first, based on the aim of a research, and then take its logical negation to obtain the null hypothesis H0. As an example of how to state the null and alternative hypotheses, consider a claim by a light bulb manufacturer that their latest, greatest brand of light bulb has an average lifetime that is longer than their previous average of 2,000 hours. Then, the alternative hypothesis H1, the claim they hope to substantiate, is that the mean lifetime is greater than 2,000 hours. And therefore the null hypothesis H0 is the opposite of H1, that the mean lifetime is less than or equal to 2,000 hours. Then, if a hypothesis test indicates that H0 should be rejected, then this means there's a sufficient evidence to support their claim of a longer-lasting light bulb. Once the hypotheses H0 and H1 have been stated, what we need to do in order to test these hypotheses is construct a confidence interval within the sampling distribution for the parameter we are testing. For example, if we are testing the mean, then our confidence interval is constructed within the sampling distribution of a mean. The exterior of this confidence interval is called the rejection region for H0. Then, we check whether our test statistic, which would be the sample mean in our example, falls within this confidence interval, or does it fall within the rejection region. If it falls within the rejection region, then we reject H0 and conclude there is evidence to substantiate H1. Otherwise, we choose not to reject H0 and conclude that there is not enough evidence to substantiate H1. Note that there is no circumstance in which we accept H0. We either reject it or we don't. This is analogous to what happens to a defendant on trial. Either they are convicted, which means they are proven guilty beyond a reasonable doubt, or they are acquitted, which means they were not proven guilty, but they were not proven innocent either. There are two types of hypothesis test: two-tail and one-tail. In a two-tail test, the null hypothesis H0 is a statement that the population parameter is equal to some value, which means H1 is a statement that the parameter is not equal to this value. To describe the procedure for a hypothesis test, we focus on testing the mean. So our null hypothesis is that the mean mu equals mu naught. To obtain our rejection region for H0, we first choose a level of significance alpha, as we did when constructing confidence intervals. In the context of hypothesis testing, alpha takes on an additional meaning. It is the probability that H0 will be rejected even though it is valid, which of course we want to avoid, so this probability should be chosen to be small. However, there is a trade-off. By lowering its probability, we increase the probability that the opposite kind of error will be made, of not rejecting H0 even though it is not valid. Once alpha is chosen, we construct a confidence interval centered around the value mu naught, featured in H0, the value we are comparing the mean to. The margin of error of our confidence interval is exactly the same as before, z sub alpha over 2 times the standard error of a mean. If a sample mean x bar falls within this interval, then we do not reject H0. Otherwise, x bar is in the rejection region, so we do reject H0. Another way to view the hypothesis test is to map our confidence interval to the standard normal distribution. If we take the inequality from a previous slide and rearrange it, subtracting mu naught and dividing through by the standard error of a mean, then we obtain much simpler inequalities. All we have to do is check whether this test statistic falls within this interval that is symmetric around 0, rather than around mu naught. Here we can see the rejection region, after scaling and shifting to work with a standard normal distribution with mean 0. The values plus or minus z sub alpha over 2, mark the boundaries of our confidence interval, and the regions to the left and right, the left tail and right tail, have a total area of alpha, which is the probability of rejecting h0 and the probability that the sample mean x bar will fall within this rejection region. On the other hand, if x bar falls within this region, covered by our confidence interval, then we do not reject h0. Now we consider a one-tail hypothesis test. For this kind of test, both h0 and h1 are inequalities. Specifically, the null hypothesis h0 states that the population mean is either greater than or equal to or less than or equal to some specified value. As before, we choose a significance level, but for a one-sided test, the confidence interval we will construct is one-sided. That is, it is infinite in one direction. For example, if h0 states that the mean is less than or equal to some value, then the confidence interval consists of all real numbers less than or equal to this value that is greater than mu0. That is, h0 is not rejected if a sample mean is not greater than mu0 to a statistically significant degree, where a margin of error indicates what statistically significant means. On the other hand, if x bar is greater than this threshold, then we reject h0. If we transform everything to the standard normal distribution, then, as in the two-tail case, we get a much simpler inequality to check, using a test statistic defined earlier. The same is true of a null hypothesis h0, mu greater than or equal to mu0. Note that we do not reject h0 if a test statistic is greater than or equal to a negative value that indicates a threshold for statistical significance. Note that for these one-tail tests, we use z sub alpha instead of z sub alpha over 2. The reason for this difference is best explained visually. First, suppose the null hypothesis is h0 mu less than or equal to mu0. Then, as with a two-tail test, the area of the rejection region needs to be alpha, but this time, the rejection region has only one component, rather than two. This is because we do not reject h0 if a test statistic is anywhere to the left of this line. This plot is for the opposite scenario. h0 states that mu is greater than or equal to mu0. Again, the rejection region has only one component, here. Because we do not reject h0 if a test statistic is anywhere to the right of this line,